Welcome all. Welcome to class 43 of time series. See, I've written here integrated process of order 1. We'll do more later. We'll study the general ARIMA process, but for the time being, I'm using only integrated process of order 1. So if you go to the general one, you will see ARIMA. So in ARIMA PDQ, you have three components. One is AR, ARP. We'll do a part of ARP in today's class as well. We've started with AR1. We consider P to be 1 in the last class. We'll consider ARP today. Before going to ARP, I will discuss one example from AR1. Then we'll go to general ARP and we'll see under what condition ARP will be stationary. We know that AR1 is stationary. If I write like this, xt is equal to mu plus alpha xt minus 1 minus mu plus et. This is stationary if alpha mod less than 1. This is what we know by now. And I want to give you one example for this. Then we'll move to general ARP. Next time, we'll discuss the second one, that is integrated process of order Q. Sorry, PD, integrated process of order D. And in this example today, AR1, I will consider this one with D1. I've written, see here, integrated process of order 1. I will consider one example which is integrated and will apply some operation like differencing. Okay. After differencing, we'll get AR1, then we'll apply AR1 model to forecast. And then we have Q, MAQ, moving average process of order Q. We'll go to this one. Auto-regressive, you are familiar from regression. So this is what we are doing now. We have completed last time about AR1. When AR1 is stationary, alpha mod is less than 1. In today's class, I want to consider consumer price index. Suppose you know consumer price index Q1, Q2, Q3, Q4 up to Qt minus 1. These are the values at these times 1, 2, 3, 4, t minus 1. You need to predict Qt. You need to predict this one here. So if you want to predict this one, then you can use history of the process up to t minus 1. The values are available for you. You can use the values. It's not markup because we are using all these values to predict this one. So before predicting this one, you have to check whether the series is stationary or not. It is observed. Also, we'll see later through graphs, but now it is observed that the series is normally not stationary. Okay, consumer price index is not stationary. You must be knowing what is consumer price index. I'm not going to that. So this is not stationary. So what you can do here is you can apply some kind of stabilizing method. Okay, and it's seen, like I said you, that if you take log, then it changes. Okay, so this is called log transformation. Sometimes what will happen, if you find the logarithm of all these, then this is a kind of mathematical stabilization. Okay, you take numbers. Suppose I will take numbers here. I will take numbers here 1, 10, 100, 1000, 10,000, 1 lakh. Okay, then I will take logarithm. Then what will happen? If this is x, I will find log x with base 10. Okay, log 10 will be when x is 1, that is log 1, that will be log 1 base 10, right? 10 power 0 will be 1. So this became 0. How about this log 10? Log 10 is 1. 10 power 1 is 10. So this is 1, this is 2, this is 3, this is 4, this is 5. See, it's a kind of stabilizer. See the increase here from point to point. When you take log, the numbers are coming very close. Okay, I mean, it's a stabilizer. The large movements, if you see, I mean, from time to time, the decrease a lot only by taking log. So if this is stationary, this is also not stationary. That's another thing. Also remember this. Suppose I have a series like this around 2. Okay, this is stationary. This is stationary. This is not stationary. Suppose if I write 1, 1, 3, 5, 7, 9, not stationary. But if I apply differencing, okay, I want to difference. It's like the continuous equivalent of differentiation. Integration means what? There is an integrating effect. We talk about national integration. You add state starting from Tamil Nadu, you can add Karnataka, then one by one, then we go till north, I mean left, right, everywhere, wherever you want, and you complete. Okay, so that way there is an integrating effect. From 1, you add something, you get 3. There is an add-on effect. You add something, you get 5. So this is an integrated process. So if you differentiate that, what will happen? You just subtract. You get 2, 2. This becomes stationary. Stationary exactly you will not get. If exactly you get this, why to apply any ARIMA or ARMA, whatever? You don't need to apply any time series model to forecast for future. You don't need any model. But it will not be this way. The deterministic part I'm writing. In reality, it could be something like this, 2.01, 2.012, you can write 1.999, okay? I think that you need to understand something like this, 2.120, 2.015, that way, around 2. Somewhere you have a number less than 2, somewhere you have a number greater than 2. So the deterministic part is 2 here. There is a stochastic part as well. Whatever way we want the world to happen, it will not happen that way. So there will be some component we have no control in life. But for example, I have taken this way, 2, 2, 2, 2. So now this became stationary. So this process is not stationary. However, if you difference this process once, this will become stationary. So this is called I1, integrated process of order 1. There is a integration effect, okay? That effect you can do. So if you apply differencing once, it becomes stationary. So here also the numbers, maybe you will get 1.003, 2.999, 5.023. That way you will get the numbers. If you apply differencing once, if you differentiate it once, okay, you will get this way. That becomes stationary. If you start with a quadratic one, suppose you have 1 square, 2 square, 3 square. This is a series, okay? And you want to see the transformed one, transformation in the sense here, differencing, okay? This is 5 minus 1, that is 4 minus 1, that is 3 here, then 5 here, 7 here, 9 here. Still it's not stationary. You apply once more, this becomes stationary. If this is stationary, this will be I2. This will be I2, integrated process of order 2. So if you difference it once and you get a stationary series, then you can apply to this series any ARMA process to forecast the value here, the next point. And remember, you will not get exactly 2, 2, 2, 2. The points will be around 2, and you want to know what is that number around 2. If you exactly get this way, the numbers, then you don't need any model. You can say 2 next time, right? So this is I2, this is I1, integrated process of order 1. So these are the two things. After taking log also, this is not stationary. If you apply differentiation once, which is differencing here in discrete sense, this is not a continuous quantity, okay? So we are not applying differentiation exactly, but yeah, the discrete version is you just subtract, okay? If you subtract, then what will happen? 1 to 2, you will get 1 here, 2 to 3, you will get 1 here, 1 here, this becomes stationary. And it is observed that the consumer price index, this is not a stationary process. So normally, if you take log, this is stabilized. Then again, it's observed that this is I1 process. So you can apply once differentiation. Okay, if you difference, you get the first value log Q2 minus log Q1, and here log Q2 Q3 minus log Q2. That way, if you find here log Qt minus 1 minus log Qt minus 2, that way. This one, because this is I1, okay, this is stationary. So this is data. You apply log transformation, then difference once, you get the series. And this is seen that, okay, it's observed that this becomes stationary, okay. You know, not only stationary, a part of stationary, AR1. We know this. We'll just apply AR1 process. This is a AR1 process. You just accept this now. In diagram also, I think I've written something. See, there is an add-on effect. From time to time, if you get one process, if I draw the graph this way, what will happen is, you have seen this way, there is an increase, little increase here, and then increases more. So definitely, you will not directly apply any ARMA process here to predict the value here. We know the values 1, 2, 3, 4, 5, 6. We want the seventh number, but you will not definitely apply ARMA process here. This is not stationary. There is a clear indication that the series is increasing. Okay, there is an add-on effect from time to time. But the add-on effect, what is that add-on effect? That you have to know whether that add-on effect is stationary or not. Suppose we are talking about the height here. You consider one guy. Okay, you consider the height. If you consider the height of one child, okay, this guy is growing. So if you see how this guy is growing, okay, you see how this guy is growing. So here there is a add-on effect. Okay, the height definitely, if you see from time to time, you see more height from time to time. But the increment, height increment from here to here, here to here, if you see that is stationary or not, that also you need to check. That also you need to check. Suppose the growth here is 2 centimeter, here 5 centimeter, here 1 centimeter, then also there is a problem. So there is a add-on effect, that's fine. There is an integrating effect, that's fine. But the integrating effect is there. That differences if you take, okay, the increments if you take, increments of height, whether that is stationary or not, that also to observe. How can you know? You just apply differentiation. See, we got this way. So more or less you can say this looks like stationary. There is not a lot of variation here, okay, as compared to this one. So instead of directly applying ARMA process here, which is definitely not recommended, and you can't apply that, even it's ARIMA one, okay, that means it's not stationary. What you can do is, you see that after differentiating once, it becomes stationary. If it will not become stationary, then do it twice, 3 times, 4 times, 5 times, till you reach stationarity. Like this I explained here. You continue doing that. So once you get a stationary series, okay, we'll do one problem also, and we'll check, and through graphs also, when you implement in R, we'll see here using numbers. You can see now this becomes stationary after 2 times. Okay, so it may become stationary after 3 times, 4 times, 5 times. You continue doing that. Once you think that this looks like a stationary one, not by only seeing in eyes, but by applying methods. Okay, we have different methods. We can test whether it's stationary or not. So once you know it's stationary, then you can apply, you can consider one process here. Like as already I mentioned you here, this is AR1. Okay, this is AR1. So this process, you can write R1 for this, or you can write R2 here, R3 here, and this will be RT minus 1. This is called force of inflation. Remember, RT here is called force of inflation. What is RT? Or maybe I can write, yeah, let me write RT. RT is force of inflation. And what is that? Log QT divided by QT minus 1. This is called force of inflation. Instead of directly predicting consumer price index, okay, we'll apply AR1 process to RT, this one. So remember what we did? We applied log transformation, then we differentiated once, and we got this one. So now with this series, okay, R1, R2, R3, RT minus 1. Okay, this is not present though. These are the numbers. Okay, these are the numbers available. Using these numbers, we'll try to predict RT. This is our work. Okay, so using these, you have to predict RT. We'll write the formula. RT is equal to mu plus alpha. We write xt minus 1 minus mu plus ET. Okay, in time series 2, you will know how to estimate the parameters. Will not worry about that. This is an estimation of mu. We'll write here, and we'll learn how to estimate this parameter. This will be the answer. Okay, again, as I must have mentioned you before, this is not exactly RT, ET will come. You can write this as predicted RT. Okay, we have a different symbol also. So this is predicted RT. Let me write this. When you write predicted, because we are here, okay, data is available up to this, and we are predicting this one. This symbol you can use RT for exact RT that will be available when T time will come. Now we don't know. So predicted RT, when you write here, will not use the error. We'll go to the general method, but now remember this will be our answer, and you get mu cap. Okay, you have to estimate using the data available, but in the model, after substituting the estimated values, you need only x minus 1 here. Okay, here I have to write R. The series is R. I have to write R t minus 1 here. We need only this one. You put the value here, okay, and then get predicted RT. Predicted RT, if you want to get a t minus 1, you have to use the t minus 1 value. All other values, past values, will be used to estimate the parameters. So we'll use anyway all these, but in the model itself, we use only one, AR1. And later you see, this is a markup process. We say AR1 is markup. This process is markup because we are using only one step information. However, if you see these two, to estimate these two, we'll use the whole data, whatever available. AR2 is not markup because in that formula, we'll have two terms. Okay. Now, I'm not going to that. We'll come to those things later. So this was one example of AR1. Okay. Let's go to the second one. Okay. This was a part I wanted to spend 15 minutes. Now we'll go to, let me erase this. We'll discard that one. This is also not required. We'll start ARP process. Okay. Let me start ARP now. Here xt will be equal to, we start with mu here, mu plus alpha 1 xt minus 1 minus mu. You can continue this one up to alpha p xt minus p minus mu plus et. Okay. So we know xt in terms of all the previous values. In the model itself, we have xt minus 1, xt minus 1, xt minus p. So if these values are available, we have to put here. Forget about estimating the parameters. In the model itself, we are using lot of past values. So this is not a Markov one. Doesn't matter. We are not studying about whether it's Markov or not. Now this is ARP, general one. Okay. Here this process will be stationary. Okay. This will be stationary when? This is stationary when if the roots of the characteristic equation, you just need to remember the formula. How you can remember this one? You bring everything to the left. Okay. Xt minus mu, you can denote it by yt. If I write this way, xt minus mu is equal to this one, and you take yt for this, alpha 1 yt minus 1 up to alpha p yt minus p plus et. If you remember this way, and you bring all the terms to the left, and again if you want, you can write this in this form. Always it will be useful. Yt minus alpha 1, for yt minus 1 you write b of yt. So what will happen? Yt will be equal to alpha 1 b of yt here and bp yt here. That way you can write, bring everything this side and take yt common. So you get 1 minus b yt, yt minus b yt. Okay, alpha 1 also you have to write, minus alpha 2 b square yt, that way minus alpha p bp yt is equal to et. This is the process. And this one you need to remember, you replace b by z here. 1 minus alpha 1 z, alpha 2 z square. Okay, and then this, I compatible with z actually. Okay, I'm compatible with this. So this is equal to 0. This is called characteristic equation. We don't need the proof of this one. Just remember the roots of the equation, the roots of this equation. You can remember this way. All the roots, if you find, are greater than 1 in magnitude, are greater than 1 or they lie outside the unit circle, you can write, because you might get complex numbers. In that case, what will happen is the root should be outside this. Okay, if you draw one line here, then all the roots, if you see, they must be outside this one. This is one, this is one. Okay, even if you want, you can draw one here. Then if the roots are outside this, here, then it's fine. Unit circle means the radius is 1 here. So suppose you get a root half here, that's fine. You get root here, that's fine. This is a complex number. This is a complex number. Okay, we'll see. But if it goes here, suppose this is 2 plus 2y, real part is 2, imaginary part is 2, then there is a problem. But real roots you can represent using 1 dimension. For complex numbers, we use 2 dimension. Okay. Now we'll consider one example. Even we'll check that R1. We'll consider R1 example also. If you remember, we started with this one. Xt is equal to alpha mod less than 1. You start with this 1 by 2 xt minus 1 plus et. If you get this way, okay, and if you apply this formula, see how you get this equation, 1 minus alpha 1 z, alpha 2 z, and all that z square. So alpha 1 is the coefficient of this. Okay, here we have only one coefficient. So characteristics equation will be 1 minus half z, you have to write. Okay, so that you have to take 0 and you have to find the root. It's greater than 1. So z will be 2. You can write the magnitude is greater than, z modulus is greater than 1. Okay, so this is stationary. Even if you consider general alpha 1 here, what will happen? Suppose instead of this, I will consider alpha or alpha 1, whatever you write. Then what will happen? You need to find this one. We had a derivation last time for this one, and this will be 1 upon alpha, and 1 upon alpha is always greater than 1. See, we're not seeing the coefficient, we're finding the roots, we're solving equation. This is always greater than 1 because we consider alpha mod less than 1. When alpha mod less than 1, we already used, we thought that this will be stationary. Okay, when alpha mod less than 1, this is what we used last time, this is stationary. Now if alpha mod less than 1, then 1 by alpha mod will be greater than 1, and the roots of the characteristics equation, if you apply today's formula, they're greater than 1 anyway. So we verified AR1, whatever formula we use, that one is consistent with the general formula for ARP. Okay, so whatever we use for AR1, that is also satisfied here. You can consider this way: if alpha mod less than 1, AR1 is stationary, or you can directly use this one for all P. Even if P is 1, we can use this formula. This is the general formula. Now let's go to other example. This is one AR2 process. If I write xt is equal to minus 2 xt minus 1 plus 3 xt minus 2 plus et. This is the process. Okay, and you check for stationarity. The question is check for stationarity. Then what you need to do is you find the characteristics polynomial. That's all. that will be 1 plus, because you have to take everything to the left, 2z minus 3z square. You have to solve this one. If you solve this one, you will get this way. You check it. If I'm wrong, you can say minus b plus or minus b square minus 4ac. Okay, 4ac divided by 2a. Two minus 4, that is minus 2 divided by 3. I hope it's correct. Okay, 6 by 6 is 1. And the other one is 2 minus 4, that is minus 2 divided by 3 minus 1 by 3. So if these are the roots, then this will not be stationary, because both must be greater than 1 in absolute value. 1 more is 1. That's a problem anyway. You can put 1 here and check. At least for 1, it will not be stationary. Even if it's on this, okay, then it will not be stationary. Here 1. On the boundary, this is not stationary. It should be strictly greater than 1. Then only it will be stationary. 1 is the case of integrated 1. We'll go to that later. So the other one is minus 1 by 3 or 2, 5. It doesn't matter. This is not stationary. That is the conclusion. Not stationary. Okay. If I change the example a bit, if I give you the second example like this, you need not check here, because this one and this one, they are the same. Okay. xt I'll write you compare with this one. Sometimes you might get this way as well. Here you can consider xt minus 5 as xt, or you can denote it by yt. Xt minus 5 is yt. Then what will happen? Your series will be something like this. Your equation will be yt is minus 2 yt minus 1 plus 3 yt minus 2. That way you will get. So this and this, you just match the coefficients. Okay, they must match xt minus 5, and then you see the coefficients here, minus 2 plus 3. That's all are matching. So even if you find the characteristics polynomial here, you'll get the same, and you'll get these roots. Again, if this is not stationary, this is also not stationary. We'll not check it separately. Now another example. Check for stationarity once again. In this example, you have 11 upon 6 xt minus 1 plus et. Okay, this is the example. Now you need to check. So I'll find the characteristics polynomial, and this will be 1 minus 11 upon 6 z, okay, minus z square minus 1 upon 6 z power 3 is equal to 0. So now you need to solve it. Let me write power 3 here, then 6 will come, right? This is the equation. Now if you see third degree equation, so with a lot of, I'm not going to the history, okay, when a solution came, it's quite interesting. If you have time, I can share you 1 or 2 videos, hundreds of years, the mathematicians, okay. So Cardano and Targetilla, all those they tried. I mean, it took hundreds of years to get a solution of this one. Even when they found the solution for a quadratic equation, okay, a lot of mathematicians, okay, from all over the world, they combined, and then they found the solution. Because even the quadratic equation we are using, x square plus ax square plus bx plus c, whenever you get a negative root, there was no geometrical justification. That came only after this, okay. Because if you, I'm not going to that, it will take a lot of time. But normally we don't use the general method of a third degree equation, because again it will take a lot of time, 2 to 3 pages. Normally the students of mathematics, they do it in a post-grad course, but we don't do that. If you get a third degree equation in the exam also, they will give a hint. You can try with some number 2. I mean, one root will be given. Even if it's not given, you have to apply logical reasoning. You just go on putting value here. Suppose I put 1 here. 1 plus 6, that will be 7. 7 plus 11, that will be 18. 18 minus 1, that will be 17. That is not satisfied. 1 is not satisfied. You can try that way. Okay. If I am correct, I think 1 is a root. So if I check here once again, 1 minus 11 upon 6, you should get plus this one minus. Okay, so let me replace it by this. Then what will happen? This is positive. This will be negative. Okay. This will be negative and this will be positive. This will be negative. Let me write that. You check, okay, whether 1 is a root or not. You put 1 here. 1 minus 6, that is minus 5. Minus 5 minus 6 minus 11 plus 11, 0. Okay. This is the example given in the material. I remember 1 is a root. So you check 1. If 0 is a root, then you are lucky. Okay, you can take the Z common, it will be a quadratic equation. So you check for 1, 2, minus 1, minus 2. Normally in most of the questions, they give a root 1 or 2 or 3, okay, which you can check by putting here. Now that you know 1 is a root, if you put 1 here, the equation is satisfied. You know that the next term will be Z square because 1 is a root. So this is the procedure. This is not a procedure, but yeah, this is easy. You can use this one. Okay, this way you can do. We are not using any general method of a quadratic equation. So minus this you can write, then you write minus 5, this one. Because we had 6, you have to compensate, okay. And the next term will be 5Z, okay, so that again you will get this one. But we have 11, you write 6 here, take 6 common. And once you know one root, whatever way possible, either given or by general reasoning, the others you can find easily from a quadratic equation. Now that we know the roots are 1, 2, 3, this is not stationary. 2 mod is greater than 1, that's fine. 3 mod is greater than 1, that's fine. But 1 mod is equal to 1. This is not fine. Okay. This is not fine. This is on the boundary. So this is not stationary. This is not stationary. We'll try to change it to a stationary series. Okay, that is possible if it's a part of ARIMA. If there is an integrated effect, then we can change it to stationary. Okay. Let me write this. We'll try to change it to stationary. But we have to start from here. This is not stationary. This is not stationary. Okay. Then, but this is this is AR3 process, which is not stationary. Now, let me write it once again. XT 11 upon 6 xt minus 1. I think it was minus x minus 2, x minus 3 plus et. Okay. Now this is called xt minus 1. You have to find this way. Okay. How you can do that operation? If you have one series like this, x1, x2, x3, x4, you just subtract x2 minus x1, x3 minus x2 this way. This process, if you want to find the differentiation, you can do this way. This is the differencing one. Okay. So this way here, it will be yt. We'll take yt or some other ut, whatever you want. We want this way. Okay. So if you want to get this way, we'll try to take everything to the left hand side. Minus 11 upon 6 xt minus 1. And then you write xt minus 1. Then if you see, you will have 5 upon 6 xt minus 1. And if you see the second term, we have xt minus 2. We need 5 upon 6 xt minus 2. Plus, okay. Now you check that we have xt minus 1. and then minus 5 upon 6 xt minus 1 minus xt minus 2. Yeah, this is also fine. How about this? I've taken 5 upon 6, remains 1 upon 6. Okay, so 1 upon 6 minus 1 upon 6. 1 upon 6 xt minus 2. This is 5 plus 6, 1. Okay, but I had to write minus here because it was minus. I've taken this one. This is minus, this is plus. Okay, yeah, so I've taken 5 upon 6, 1 upon 6 remains, and this is minus. This is ET. Then I can take 1 upon 6 common. The next task is to denote it by some other. Suppose I will take YT or maybe some other one, because YT we take for a different purpose. There might be confusion. So let me take WT. Okay, is this one. Then my new series will be WT minus 5 upon 6 WT minus 1 plus 1 upon 6 WT minus 2. That is equal to ET. Okay, this is the series. If you want to see this way, you can write equality sign and you can write minus here. That's all. This is the AR2 process. Okay, this is AR2 process. You see here we have a AR3 process. Now we have AR2. Okay, we have AR2 process, but we want to see this way. We have the terms in the left hand side. Okay, that's a separate thing, and we'll check the roots now. We'll solve this one. 1 minus 5 upon 6 z plus 1 upon 6 z square. Then you will get z square minus 5z plus 6 is equal to 0. If you solve this, you will get 2 and 3. Both are greater than 1 in magnitude. We don't have complex numbers, so we need not worry. If you get a complex number, complex root, you have to take them all this way. And there is a formula. If you see the complex number, you have to find this way. That is the only difference. Real roots means if there is a negative, it will be positive. That is absolute value. You will do questions, you will be able to know how you will get roots, but here both are greater than 1. So this is stationary now. Okay, if you consider this AR2 process, if you consider this process AR2 process, this is stationary. So you can apply the method here. Okay, ARIMA. So I can write WT is equal to 5 upon T WT minus 1. Okay, minus 1 upon 6 WT minus 2 plus CT. This is the AR2 stationary series. Okay, this is AR2 stationary series. You can apply the general method. Okay, we'll go to the general method in time series 2, and you can forecast using this one. This is stationary. Okay, so no integrated effect is here, but here you have integrated effect. Okay, so if you want to term this one, now we don't have MA part here, moving average part. Moving average MA will start later. We have not started even. If you want to classify, because that is also a part, we'll see next time. If you want to classify this one, it will be ARIMA, not ARMA. And we differentiated one, so it will be one, no MA part. Okay, and here you have to write this one. ARIMA, when you write, you check about this one. Forget about this part now. You differentiated one, so you have to write once. If this is not stationary, then you can do once again. Okay, and then you have to change it to 2. If you differentiate this 3 times, you change this one to 3, the middle part. Okay, 1 means you have to differentiate once. Now check the parts here. If you want to term this as ARMA, okay, ARMA, MA part is 0 anyway. There is no MA part here. AR part 2. So this is ARMA 20, or you can write AR2. I've written AR2. You can write this as AR2 or ARIMA 20. No MA part here. You can write this. How about this? It doesn't matter whether this is stationary or not. Okay, it's a stationary series. That's a separate thing. If this becomes stationary, you have benefit here. You can write this as ARIMA, okay, 20, not 3. See, I started with AR3 if you remember. Now it will be ARIMA 210.
So,
Yeah,
sir, if a series,
yeah.
even after say doing multiple differentiations, doesn't become stationary, then
Hmm.
we can't call it an ARIMA process, right?
No, you can't call it ARIMA process. It has to become stationary finally.
Okay.
ARIMA, see, ARIMA, from ARIMA, you get to ARMA. Okay. So when you get to ARMA here, you have to see the terms, whatever number of terms that you have to write. Then it becomes ARMA 20. So this one is ARIMA. I think there is still some problem. I didn't get you. Repeat once again your question.
Yes. So, sir, I'm saying that if a series, like if it's a auto-regressive series of any order, and even after multiple differentiation of the series, we don't get a stationary series. Like even if trying it for 10, 11, 15, 20 times also, like differentiating, the series doesn't become stationary. In that case, we can't call it ARIMA, say, ARIMA 5, 2, 0. If it doesn't get stationary, it will ultimately be ARIMA 5, 0, right?
Yeah, it might not be because there are other effects as well. We'll see later. If you want to achieve
Okay.
stationarity, what will happen? So we'll see. We'll go to that. Sometimes what happens is you don't have integrated effect, but you have some other thing like seasonal, or maybe there is something like there is a strong doubt. This is not integrated. This is not integrated. So non-stationarity could be due to any of the reasons. This is one of the reasons. So normally what we think, normally if you ask students or maybe people, they will say ARIMA is non-stationary, ARMA is stationary. But what I am saying is ARIMA is not only form of non-stationarity. There could be other forms of non-stationarity as well. Okay, so those things we will consider. The normal trends, like if you go to a doctor, normally they check for fever and small problems like 4 or 5 problems. In 80% of the cases they are resolved. Okay, that way we'll see the different kind of stationarity normally we see in practice, and we try to remove them. So we are removing here the non-stationarity by differentiating. You go on differentiating till it becomes stationary. Okay, now that this becomes stationary, like going by your question, now ARMA 20, we checked this is stationary, and now we have a classification ARIMA this. Okay, this is what I said, and you are also correct. And we'll do all other things also later. So
So,
that
but
means
if a series doesn't become stationary at all, like whatever we do, even if
that's what I
the other.
said. So it will not become stationary. That means you should have some other problem. See, normally what happens if people go to a doctor, they give medicine, paracetamol here and there, then still you have fever, then they check for malaria, typhoid, and all that. Similarly, if it will not become stationary, it will not be ARIMA. It's a non-stationary process of some other form. There are various forms of non-stationarity. Here in time series 1, we're talking about only one form of non-stationarity, that is ARIMA. Suppose you differentiate 3 times, 4 times, 5 times, 6 times, it's not becoming stationary. That means what? It's not from ARIMA form. You don't have a ARIMA series. So in that case, what you can say is you have ARMA plus some other forms. Okay, we'll check all these. Okay, there are other 3 to 4 types of forms. Like we have one example in time series 2, greeting card sales. Okay, what happens is normally if you see every January and December they increase, but here if you see every you see season. Okay, this is seasonal. If you want to forecast here, definitely will not take the data, continuous data. We'll take with 12 lag, all that. So what we see is there are some seasonal component, there are different components. We'll see other forms of non-stationarity. Now we are doing ARIMA. It's ARIMA means what? After differentiating many times, it will become stationary. That's all. If it's not becoming stationary, then it will not be ARIMA. Got it?
Yes, sir.
That means if I extend it further, suppose here we stopped, right? Even we have questions you will see later. I think you have questions. Yes, we have questions in our material where you have to differentiate it twice. Why twice? Why not once? There your answer lies. ARIMA 20. So this is ARIMA 210. This is the classification because we don't have any MA term. We'll not worry about that. This one. And also remember in notation, if you want to use notation instead of this one, you can write this. Okay, we write nebula. We write nebula xt minus 5/6 nebula xt minus 1. plus 1 upon 6 nebula xt minus 2. And if you do it twice, we write square here. Okay, this is the transformed one. After doing once, we check it stationary. So this is the ARIMA 20 stationary one. That's why this is ARIMA 210. That this thing, this one, how can you know? What you can know is, if you differentiate it once, it will become a ARIMA 20 stationary series. Okay, if it becomes stationary after differentiating one, this is not stationary, but if you differentiate once, it becomes stationary, then this will be ARIMA 1. If it will become stationary after differentiating twice, if you differentiate twice, it becomes stationary, then we'll write a 2 here. Okay, but if it's from ARIMA, then only this will happen. It might not happen at all. We don't know. We'll see that in time series 2. If we try time and again also, it will not become. Then we'll see the other problems. We'll check for other problems. Now that we are in the ARIMA, then this will happen. Even if you apply all the seasonal component, everything will study later in ARIMA, that might not work. In that case, because in CT6, I mean in part of CS2, we are doing only the linear stationary series. All right, then class is over now. Thank you.
Thank you.